The goal of this video is to understand and apply the relationship between force, mass, and acceleration. When you push or pull on an object, you exert a force onto it. The force can come in many different forms, but will always be proportional to the product of the acceleration the object has and how much inertia, or mass, it has. Mass is measured in kilograms, so the dimensions of force are kilogram meters per second squared, which we call 1 Newton. The acceleration an object has always points in the same direction as the force causing that acceleration. For a projectile without air resistance, no acceleration in the x direction means there's no force in the x direction. An acceleration downward means there's a force pointing downward. If the acceleration on an object is the acceleration of gravity, g, then the force must be the mass of an object times the acceleration due to gravity, mg. This is what we refer to as the weight of the object. There might be more than one force acting on an object at any given time, with each force tending to cause an associated acceleration. The net force acting on an object is equal to the mass of the object times its resultant acceleration. The net force of an object is just the vector sum of all the forces acting on the object. If it works out that all of the forces acting on the object are equal and opposite, then the net force on the object will be equal to 0, and the object will undergo no acceleration. The net force is a vector sum, so if two forces acting on an object are pointing in two different directions, the net force will point in the direction of the sum of the two vectors. The acceleration, then, will be in the same direction as the net force. Let's call upwards the positive j direction and rightwards the positive I direction. If the first force is 4 newtons to the right, and the second force is 3 newtons upward, then the net force must be 4i hat plus 3j hat. If we know the mass of the object to be 5 kilograms, then we can calculate the acceleration the object will undergo as 4/5 I hat plus 3/5 j hat, which would have a magnitude of precisely 1 meter per second in the direction of the net force. Consider this object being pushed along a frictionless floor. The net force acting on the object in the horizontal direction is the force from the push, so the object should accelerate in that direction. The object is not accelerating in the vertical direction, so the net force in the vertical direction has to be 0. However, we know there is at least one force acting on the object, the force due to gravity. Since the object isn't accelerating downward, there must be another force acting on the object to cancel out the gravitational force. This will be from the floor, pushing upward against the box, just as your chair is pushing upward on you as you sit on it. The net force in the vertical direction, then, must be the sum of the gravitational force and the force from the floor, and they have to add up to 0. This sort of contact force with the floor is what we normally call the normal force, or F sub n for short. Normal is math talk for perpendicular. If the floor is tilted, the normal force will always be perpendicular to the floor. Gravity, on the other hand, will always point vertically straight downwards. Consider two boxes placed next to each other. It is important to note that the net force in Newton's second law refers to forces external to the system we are considering. If we consider both boxes together as a system, then the only forces we need to consider are forces coming from outside the boxes. The boxes cannot cause themselves to accelerate. The mass in Newton's second law is all of the mass inside of our system. A second force acting external to the system would just be added in as normal. Let's consider a completely different situation. Here's a mass hanging from two strings of unequal length, such that one forms an angle of 45 degrees to the horizontal, and the other forms an angle of 60 degrees to the horizontal. We'll assume that the strings are light enough they don't have to worry about their mass, and strong enough not to break. I want to calculate the tension in the strings. A force due to gravity will act on the box, and both strings will apply a tension force to the box. We'll abbreviate these forces as T1 and T2. We can break the forces down into x and y components. Let's call rightwards positive x and upwards positive y. Since I know the box is at rest, I know it has 0 total acceleration. Its acceleration in both the vertical and horizontal directions is 0. This also means the net force in the x and y directions are both separately 0. Knowing this, I can determine the tension in the strings by working in each direction separately. Let's start with the y direction. The sum of all the vertical forces is T1y and T2y acting upwards, and the force due to gravity acting downwards. The force due to gravity is the mass of the object times the acceleration due to gravity, or mg. Then, since I know the angles that the string makes with the horizontal, I know that the sine of theta 2 is T2y over the whole tension T2. The sine of 60 degrees is root 3 over 2, so I can rewrite T2y in terms of just T2. I can do the same thing for the string on the other side, where theta 1 is 45 degrees, and the sine of 45 degrees is root 2 over 2. Then I can plug in these values into my net force in the y direction to obtain this expression. And this is as far as I can get with the y direction for now, so let's have a look at the x direction. The sum of all the forces in the x direction is T2x pointing rightwards and T1x pointing leftward. I can use the cosine of the angles to get these components in terms of the total tension, and then plug those into the net force in the x direction, and we discover that T1 is T2 over radical 2. This I can take back to my equation over here. Substitute T2 over radical 2 in for T1, and obtain an expression for T2 in terms of just the mass m and a bunch of constants. So indeed, if you know the mass of the object, Newton's second law applied to both the x and y directions will allow you to determine the tensions in both the strings. In general, all of Newton's second law problems can be solved by working with forces in the x and y components separately.